This is the last session, and it's entitled Exposing Bootkits with BIOS Emulation. And the speaker today is Lars Hockley. And thank you, and I'll turn it over to Lars.
Thank you very much, Chris. Hi guys, thanks for showing up. I know it's getting late and you probably have some other stuff you want to do in Vegas as well, but I really appreciate you guys showing up. So my name is Lars Hockley. I work for Bootkits, which is an American company, but I'm actually based in the great city of Oslo, which resides in the perfect kingdom of Norway. And it really is a great place to live because it's somewhere where I can actually reverse engineer malware for a living, which I love to do, right? And I really love the fact that someone will actually pay me money for doing it. Because this means that at the end of the day, I can pay the bartender, right? So everyone's happy. So I've always been more interested in the actual techniques that malware makes use for, instead of more than who's using the malware for what purpose and who they're targeting and so on. And I really enjoy coming up with techniques to sort of counter their techniques. Today I'll show you a really fun approach to detect some really nasty kernel mode rootkits that manage to compromise 64-bit versions of Windows by manipulating the boot sequence. So I want to start out by actually saying big thanks to Microsoft for really beefing up the security when it comes to protecting against kernel rootkits in the more modern versions of the operating system. Because what they've done is to introduce some features that really raise the bar for kernel rootkits. And so we've seen that a lot of the rootkits have actually moved into user mode, which makes them much more easy to bypass, and they're not really a big problem anymore. So the main, probably like the main feature, or like the most important one, I would say is driver signature enforcement. Because from the rootkit's point of view, this makes it much harder for them to actually run code in kernel mode. And if you want to be a kernel mode rootkit, then you have to run code in kernel mode, right? So the other thing they've introduced is patch guard, which will make it much harder for a rootkit to actually manipulate something in the kernel, which is what they typically like to do. They like to hook system calls, they like to modify some low-level operating system structures or whatever in order to fake stuff or, yeah. And also they have made some steps in order to ensure that during boot time, only trusted modules are allowed to load, which from the rootkit's point of view means that it's much harder for them to implement persistency. Because if you're a rootkit and you don't manage to load during boot, then you're not really a really sophisticated bootkit. So why then? Why are techniques that really come from like the 1980s still a threat today? Because I mean, targeting the boot sectors is not really a new thing, right? You can trace it back to like Elk Cloner maybe in 1982, Brain Virus in 86. Like, it's a different implementation, but the idea is like still the same. Like, you want to modify the boot sequence in some ways that you can run code before the rest of the operating system loads. So the problem, right, is that the way they ensure that only trusted modules are loaded during boot is really a UEFI feature. It's a matter of ensuring that you're booting from signed firmware. But for systems that are still using the old legacy BIOS, you're actually trusting the contents of boot sectors that are in unsigned sectors on disk, right? So you're sort of trusting them, and at the same time, they can actually be modified. And this is what malware would do, right? It will try to manipulate them in some ways so that they can run code before all of this new fancy features kick in. So maybe it wasn't such a good idea to just load your modern, fancy, shiny OS using technology from the 1970s. So I just want to start out by just giving you a roadmap, just an overview of what I'm covering. So we start out by discussing how we can manipulate the BIOS boot sequence, as well as just how it actually works. We dive into something we need to do, which is to read the true disk contents. Because, rootkits being rootkits, they have a tendency of faking stuff. So it's no point in having like a really clever ID or a nice way to analyze the boot sectors if you can't really read what's truly there. And we're planning on doing this in a scenario where we might be running on a compromised system, right? So we move on to discussing how we can emulate the boot code in order to analyze its behavior and look for anomalies that we can use for detection purposes. Then I'll show you a demo just to give you an idea of how a typical bootkit will look like when it's emulated. I will be discussing some heuristic detection techniques based on the anomalies we observe. Towards the end, I'll show you how we can use this same approach in a way to disable the bootkit in order to regain control of the system. And finally, I'll mention a few challenges with this approach when it comes to non-standard bootloaders. So the first question would be, okay, so we know that all bootkits will modify the boot sectors, but why do they do this, right? What's their aim? What are they trying to achieve? So the thing is that they really aim to load an unsigned kernel mode driver, even though the security policies prevent them in doing so. So they want to run some code in kernel mode. So really, manipulating the boot sectors is just a way to achieve this. And also it gives them an opportunity to run before any of the new fancy features kick in, which means that they can disable them or otherwise bypass them. So most rootkits will actually modify the master boot record, but the attack surface is actually slightly bigger. There's roughly 17 unsigned sectors on disk that can be manipulated. So it consists of the master boot record, the volume boot record, and the initial program loader, otherwise sometimes referred to as just bootstrap code. It's just roughly 15 sectors which just contain code. But the challenge is, of course, they can't, even though they can manipulate this, they can't really load a driver this early, because it's really inconvenient to load a kernel mode driver before the kernel itself is loaded. So if you look at how they actually achieve this, it will vary across various rootkit or bootkit implementations. So just an example, TDL4 was the first rootkit to successfully compromise 64-bit versions of Windows. Did so by, first of all, replacing the master boot record, and eventually replacing the entire contents of the DLL that was loaded by the kernel, so that it would be able to run some code at a later point in the boot process. A more recent example of Rovnix did some kung fu patching of boot manager and then ninja'd its way, like sort of using debug registers and whatnot, sort of crawl itself onto the system. So this all varies, but the common thing is that they must modify the boot sectors. So that's what we focus on. Just a quick overview of how the boot sequence is supposed to work. So sometimes when you power on your machine, you probably see like a power on self-test thing. At the very end of this, there will be code that issue BIOS interrupt 19. This instructs the BIOS to load the first sector on disk into memory at address 7C00. So this is a segmented memory address, which is really confusing. It's confusing to work with and everything. But it means that the code segment is set to 0, and the offset is set to 7C00. And this will always be the case. So the code in the MBR expects to be loaded here, and there's no relocation or anything. It has to be loaded there to work. The MBR consists of 16-bit code designed to run in real mode. This is before even though you're running a 64-bit CPU, you will actually boot up in 16-bit, and then boot manager will flip the CPU over into protected mode and set up everything. So the MBR seeks to load the next stage, which is the volume boot record. And actually seeks to load it into the same address where it's currently residing. That means it has to overwrite itself, which is, I don't know, funny design, but maybe it made sense in the 70s or something. This means that in order to do this, it has to copy itself to a different memory location and then load the VBR back into where it used to reside. Then it passed control to the volume boot record, which loads an additional 15 sectors of code, which I refer to as the initial program loader, which will parse the file system to locate a specific special executable called boot manager. And now the boot manager is actually digitally signed, so it can't modify this on disk, right? So if you see the bootkits, they do want to replace some contents, but they have to replace either the MBR, the VBR, or the IPL. But they still need the OS to load, right? So the thing is that what they normally do is to modify something and then just resume normal boot operation. And this is sort of a fundamental thing, and it will show up when we later on try to see the anomalies of it and see if we can detect if something is bad. So this is just an illustration of how we expect the boot process to work. You can see on the left-hand corner-ish, the MBR has been loaded into memory at 7C00. Because it seeks to load the VBR into the same place where it's actually residing itself, it will typically copy itself to a different memory location. And from there, it will locate the VBR and load it, then pass control to it. And the VBR will load the initial program loader into memory, and just basically consecutive memory addresses, and run that, which would parse the file system to locate boot manager, load everything, entire contents of boot manager into memory, and pass control to it. So this is the process we aim to analyze, really. So from here on, everything that is being loaded is signed on disk. So, big problem, right? Rootkits being rootkits and all that, they like to hide stuff. So in order to sort of make sure this will work across as many bootkit implementations as possible, we really need to ensure that we can be able to read the true disk contents on a system that is potentially compromised. And I don't want to sound like someone who's announcing a limbo contest or anything, but you forget about use mode. It's all about how low can you go, right? So what you see here is an illustration of the Windows storage stack. So you can see requests coming in from user mode. Also, even if they come from kernel mode, they will go through NT-read file, which resides in the system service descriptor table, commonly known as SSDT. It used to be a war zone, more or less, in XP. Everyone was hooking there, legitimate programs, malware, you name it, like daemon tools, whatever, grayware, everyone's hooking there. But thankfully, on 64-bit, they've actually introduced PatchGuard to protect it from modification. So as the request goes down the chain, it will go through various subsystems, right? And the request will be sent down using a I/O request packet, an IRP. So eventually, it will end up in the disk subsystem, which sits just on top of the hardware abstraction layer. And now the disk subsystem is divided into 3 parts, where the lowest level part is the miniboard driver. Okay? So the miniboard driver is responsible for implementing hardware-specific logic to read and write to raw sectors on disk, which is pretty much what we want to do as well, right? So whenever the request is passed down, the I/O manager, which is part of the kernel, will call the dispatch routine, which is set up by the miniboard driver at load time. And it will call the dispatch routine that is registered to handle IRPs of type internal device control. So instead of coding up everything ourselves, why don't we just use this? This is a really nice, cool routine to use, right? And yeah. So the miniboard driver will set up the driver object. This goes for any driver on Windows really will set up its driver object when it's loaded. And the driver object contains a major function array, which is an array of function pointers to the various dispatch routines that are supported by that driver. So this means that if we can obtain the miniport's driver object, we can actually extract a function pointer to a routine that does exactly what we want it to do, right? That reads and writes to raw sectors on disk. Meaning that we don't have to worry about any hooks that might be present at like higher levels. And it also gives us it also means that we don't need to implement hardware-specific logic ourselves, which is a great thing because it can become somewhat tricky. If you want to see like an alternative approach for doing this, I did include a proof of concept code to use programmable I/O in my white paper. It's basically just using in and out instructions, which is like going even lower, right? But it has some challenges when it comes to supporting disks, basically. It doesn't support all disk types. So I actually prefer using the miniport's dispatch routine instead. So another challenge, right? This is a really powerful routine. So if I like it as someone who's trying to design anti-rootkit stuff, then you can be sure that the rootkit authors would like it as well. It's a great place for rootkits to install hooks. And some of the more sophisticated rootkits/bootkits will actually do this. So we need to get around this somehow, right? We want to support even the more like sophisticated, the fancy ones. So what the rootkit will do is one of two things, right? It will either replace the address of the dispatch routine in the major function array within the miniport's driver object in memory. Or it may also find the dispatch routine and then decide to replace some of the contents of it in memory, typically inserting a branch instruction at the very start of it, which will, once the routine is called, it will transfer control to the hook destination. So it serves the same purpose. It's just a bit harder to sort of detect and bypass. So this all means that when we're running on a system and it might be compromised, we don't really know. So we need to obtain the original function pointer. Okay, so this is sort of unfair because the rootkit, you can just replace it, but we sort of have to go through painful things in order to obtain the original ones. So whenever you design anti-rootkit things or anything, it's a good idea to just be paranoid, right? So never trust memory contents. Instead, we need to locate a trustworthy source of information. And if you think about it, all drivers on 64-bit versions of Windows are actually signed. So if we use a signed miniport driver on disk, we can use that as our trustworthy source of information, right? So our approach for doing this is to analyze the miniport driver on disk. And we aim to retrieve the relative virtual address from the disk image. And then we have a look at, okay, where is this loaded in memory? What's the base address where it's loaded in memory? If you combine those two, voila, you have the original function point. Okay, so how do you go about doing this? How do you analyze the miniport driver on disk in order to locate the RVA of the original dispatch routine? So actually, it's slightly tricky. What you see here is a simplified example of a driver entry routine. So this one will be called, it's the entry point of the driver, basically. So whenever it's loaded, this routine will run. And a very typical thing is that the kernel will pass it a pointer to its driver object, and then it's up to the driver itself to sort of register the dispatch routines for all of the various IRP types that it supports. So obviously the driver entry is an exported routine, but the dispatch routines are not. Okay? These are non-exported internal routines within the disk image. So how do you find them? So our approach for doing this is to search for the instructions within the binary itself that initialize the major function array. So if you manage to find these instructions that basically implement what I showed you in C, just we do disassembly stuff on them, you can actually retrieve the RVA of the dispatch routine which we are looking for. So we do this by recursively disassembling the driver and disk. We have to do it recursively because the instruction might reside in a local function or in a subroutine. And then we look for instructions that modify memory. And luckily, there are some common logic among the various miniboard drivers out there. So we can use that in order to find it. So this is a disassembly of an actual miniboard driver, 64-bit. So you can see that the logic actually is pretty much similar to what I showed you in the simplified example in C, right? So it will basically set up the various dispatch routines. So you see, oops, that guy. This guy is the guy we're looking for. And you'll see that it will load the address of the dispatch routine into RAX, and it will move it into some memory pointed to by RSI plus an offset. And this sort of pattern repeats throughout, right? So in this case, RSI is actually pointing to the driver object. And the thing is that these offsets are not random at all. They're actually offsets within the driver object structure, right? And that doesn't change, at least not for the same operating system version. So our approach for doing this is to first of all analyze entire routines. And we look for instructions that are something like move some routine into memory pointed to by a register plus an offset. And in order to catch the example I just showed you where the address itself is loaded into another register before this happens, we also keep track of important or interesting registers as we progress through the disassembly. So the critical observation here is that some routines will always be present. Because the challenge, right, you can't just look for move RSI plus E8, because that can be, God knows what sort of structures are being used. I mean, it can be anything. So you sort of FP as you're trying to look for the instructions that initialize the driver object. You might find something else. So the critical observation is that there are at least 5 dispatch routines that will always be present, and these will all have the same offsets every time, right? So it's power, PMP, device control, internal device control, and always driver on load. All drivers will have that. So we search for all 5 of those offsets with a corresponding dispatch routine within a single routine. And if we find that, then we can extract the RVA corresponding to the internal device control guy. And be pretty sure about, having obtained the right one. So in that way, now we've obtained the original function pointer, meaning that we can bypass the function pointer hook. But actually knowing the address of the routine on disk also enables us to detect and bypass the inline hook version, where the memory contents is actually modified. And we do this by comparing the disk contents to the memory contents, right? So if you can detect discrepancies, if you see what the routine on disk, you sort of know what it should be in memory, and then you can sort of detect that something is wrong. And also you can use the same information in order to bypass the inline hook. So the way you do this is actually you borrow or you steal a couple of instructions at the start of the routine, typically, and then you insert a branch instruction afterwards that will jump to the next instruction in the modified routine in memory, so that it will sort of execute your code first, and then we jump to the rest of the unmodified routine. So it's sort of like just a mechanism to avoid being caught by the inline hook. That way, execution will never reach the hook destination, so you will bypass it. So just a few points on how you actually interface with the dispatch routine. You sort of pretend like you're the driver that sits just on top of the miniPort driver. Normally, the miniPort driver will expect to be that the IRP is passed down to it, and when it's done, it will pass it back up. So we'll just create an IRP and give it to the miniPort driver, or at the same time registering an IO completion routine so that we get called when it's done, and then we just destroy the IRP afterwards. So there's a few details on how you do this. I think I just want to refer to my white paper. It's not really, it really boils down to just specifying the sector number, right, as a logical block address. But you also, you check my white paper. All right, so now we finally know how to read the true disk contents. So you want to use it or something, right? And you want to detect bootkits. Obviously, what we aim to analyze is the boot code itself, and we know that the boot code will make use of interrupts. Basically, it will call the BIOS to do its heavy lifting. So we need to emulate both the boot code and the BIOS, which is fun. So what we've done is to write our own custom BIOS in 16-bit assembly. Now, it doesn't implement like the entire functionality of a BIOS, because we're not really interested in booting the entire system. We're just interested in analyzing the start of the boot process, right? So you implement what you need to do, and then you just register dummy routines for the rest. So you just keep emulation going, basically. Now, I won't talk much about the emulator itself. I'll just say that, of course, it will have its own separate memory space, which is accessible to the boot code we're analyzing, as well as, of course, the emulator itself. What we do, we start out by reading the MBR, using our fancy anti-rootkit disk.io thing, load the contents of the MBR into emulator memory, where it expects to be loaded, which is 7C00. And then we load our custom BIOS into emulator memory at the very high ranges of it, which is where the BIOS usually resides. And then we start emulation at the BIOS entry point. And this is basically just a thing of convenience. It's so that we can run some init code in the BIOS before passing control to the first instruction of the MBR. So the init code will set up the interrupt vector table, which is located at address 0. This is a structure that holds all of the interrupt handlers. So it's very much similar to the IDT in protected mode, with DOS used and all that. So we register interrupt handlers for video, disk.io, and keyboard. So those are the ones we're interested in, pretty much. And for the rest of them, you just register dummy routines that would just issue like an IRET, just to make sure that emulation continues. They don't really do anything. So this means that, of course, when we emulate an interrupt, our BIOS will handle it. But for some interrupts, like the interrupt 13, it's a bit more complicated. So at this point, we actually break out of emulation. So whenever we encounter an interrupt 13 in the boot code, our emulator will pass control to the handler registered within the IBT, which will then pass control to our BIOS. And the BIOS will check which function code this is and determine whether or not it needs to break out of emulation. And if it does, as is the thing for interrupt 13, it will just tell the emulator, like, you need to read sector 1 and load it into this and this address. And the emulator will go and query the contents on disk from the anti-rootkit module, and then just write that into emulator memory and just continue. So let's try a live demo. So this is a compromised system. There's a bootkit running here. What we've done is to put a simple debugger UI on top of our emulator, so you can sort of follow what's going on. Yeah? And you can see at this point, we've already run our init code. You can see here at the address 0, the various interrupt handlers are already registered. So let's see what happens. So this is a bootkit that has replaced the MBR. So the first few instructions we will run now are actually the bootkits. It's like a bad MBR, right? So you will see that it starts out by really looking like a normal MBR, right? So I told you it wants to copy itself to a different memory location. This is it, right? Rep moves, copy itself to a different memory location since it wants to load something else into where it's currently residing later on. It will then transfer control there. And now, there's some funny things in here. If you see what's happening now, do anyone recognize what this is? I mean, if you unpacked packers and stuff and debuggers, you will immediately see that this is actually a deobfuscation loop. And if this was my system and I saw a deobfuscation loop in my MBR, I would freak out. Like, honestly, that's not a good sign. Obviously, they do this in order to complicate signature-based detections, right? So it's just like a simple, like super simple encryption thing where it's just rotating a byte in each iteration of the loop. So moving on, we will see that it will eventually call an interrupt 13. And this will now transfer control to our BIOS. You see, like we're quite high in memory. So the BIOS in this case just checks which function code it is. And then calls out, you can see here it's called out to the emulator in order to query some drive parameters. Basically, how big is the disk and all that. That's what it needs to know. And then we will indicate success by clearing the carry flag. Like, this is sort of, it blew my mind when I did this, because I'm so used to like return codes being passed in EAX. Like clearing the carry flag was just weird for me, but yeah. I guess it made sense in the 70s. So moving on, we just step over this guy. You can see some really interesting thing, right? So we're actually expecting like a regular boot sector will actually load VBR at this point. But this guy actually loads the very last sector on disk. So this sector, so I know the system, is actually outside of the normal file system. And this, under no circumstances is a good thing. I mean, you should never load anything here. So from here on, let's see, continues to load a few more. And then you'll see something quite interesting here. This is cool. So just pay attention to our IVT, which is where we registered our really nice interrupt 13 handler right here, right? This is our interrupt 13 handler. So now what happens? Bang, bang. So it just replaced our IVT, or our interrupt 13 handler in the IVT. It's not very nice of him. Not very nice at all. So now you've seen that it actually hooked interrupt 13. From here on, it will load the original MBR, which it actually had encrypted in some of the weird sectors on disk. And then it will transfer control to the original MBR. So now it's already done its nasty things. It just wants to let boot process continuous, as if nothing has happened, more or less. So you can see here, like the original MBR is doing something very similar, copy itself to a different memory location. Go there, and from here on, if you just follow the log view while I sort of step over, you see that it found the VBR, loaded it back into 7C00 again. It will then jump there. Soon. Here we are. And so the VBR, I'm just going to step over here, so just pay attention to the log view. You see that the VBR will load the IPL. It loads 15 sectors containing just code. You can see they're all in consecutive memory addresses and consecutive sectors on disk. Then pass control to the IPL, which starts to parse the file system. So eventually, it will find boot manager. Bang! There you go. It's kind of a big file, so quite a lot of reads. So now boot manager is loaded into memory, and it will simply proceed to dumping there. Kaboom. So you can see now, actually even printed it here, emulation ended. At this point, we're at the first instruction of the MBR. No, sorry, the first instruction of boot manager. And we don't really need to emulate anymore because we already have enough proof, so to speak, in order to determine, or enough information in order to determine if this is good or bad. So we've seen a couple of things, right? We saw an interrupt 13 hook. We saw it had a weird deobfuscation loop, and I was reading sectors like in the lost parts of the disk, which should never happen for normal boot code. So again, you can see that if you emulate the boot code behavior and study it, there are anomalies that you can detect, or use for detection. And what I really like about this approach is that you don't really require a baseline of it. You don't really need to know if what the boot sectors used to be. You just run it and just sort of analyze the behavior of what is currently on the system. So in other words, you don't need to know anything about the system before you run your detection code on it. So what would you hook interrupt 13? I mean, you saw it in the demo, you saw it hooked interrupt 13 or modified the interrupt 13 handler. Why would you do this, right? So the thing is that the boot code really seeks to patch modules that have not yet been loaded. So when it's running, it needs to regain control at a later point in time. And by hooking interrupt 13, whenever there is a disk operation from this point on and forward in the boot process, the Bootkits code will be called. And this enables it to actually patch memory on the fly as it's being transferred from disk into memory, right? This is the way it will actually patch memory of modules that hasn't been loaded yet. Obviously, it needs to regain control later on in the boot process because what it wants to achieve is to load the unsigned kernel mode driver, right? So it needs to regain control at some point after the kernel has loaded. And there's plenty of ways to do this. But the point is that when you emulate it, you'll actually, the boot code will actually interface with our BIOS. And, I spent a lot of time actually writing the interrupt 13 handler. So, I get upset when it sort of comes and replaces it. But the thing is that, it's quite easy to just check if our IVT is still intact after we've done the emulation. So if you see that it's been replaced, you know that something fishy is there. So you can actually use this for detection purposes. So another thing you can use is to look at boot manager. Okay, so this is a signed executable on disk. And obviously it's signed for a reason, right? It's not supposed to be modified. That's the whole point. And when we reach the last state of our emulation, you will see that entire contents of boot manager has been loaded into memory. And boot manager is a very special executable. It means it's not a PE file, so it's not loaded as a PE file. Instead, it's just loaded byte for byte. So you would expect that the disk image would be identical to the memory image. So the way you sort of detect this is just to read the boot manager file on disk and then just do a mem compare with whatever is in the emulator memory, right? So the detection is a mem compare. It's quite simple. Normally, if you detect that the boot manager has been modified, you will also see that interrupt 13 has been hooked very often. So now you have two indicators of something being bad. The last thing I want to point out is, since Bootkits really need the OS to boot, they want to make changes, right, and then let the normal boot sequence continue. The way they do this is that they store the original MBR somewhere, so that when they're being loaded initially, they can retrieve the original one and then pass control back to it. And this results in a quite interesting anomaly, which we can see when we emulate it. So you see up here, this is the first guide to be run, which would be the bad MBR, right? So as we saw in the demo, it would still copy itself to a different memory location, do something fishy, and then load the original back to where it used to be. And from here on, like the entire, everything in this area will be the exact same as what we expect it to be. So the question is, how do you detect that this is bad? And the answer is, it's really quite trivial. I mean, because if you count the number of times that 7C00 has been emulated, you will know, right? So in this case, you will see that 7C00 has been executed 3 times. But in a normal case, we would expect it to be executed 2 times, because that's like the way the boot process works. So that's our detection right there. Count number of times 7C00 has been emulated. Simple, right? So combining these 3 techniques is actually really, really successful. It's really good at detecting bootkits. But it's also useful for actually disabling the bootkit as well. So if you want to regain control of a compromised system, what you need to do is to sort of prevent the malware from loading during boot time. And that goes for any sort of malware. For bootkits, this will mean that you need to break their load chain in some way. All right? So how do you do this? If you can somehow manage to retrieve the original contents, so basically what the boot sectors should look like, and then you replace the modified parts with the original, then it's just simply, rebooting the system, and the bootkit will no longer exist. Oh, it wouldn't, no, it would probably, at least it wouldn't load. That's my point. So the key is really to determine what has been changed. Okay? And we already know this because we were smart enough, so we counted the number of times that 7C00 has been executed. So if it's 3 times, we know that the MBR has been replaced. So in that case, we actually just emulate it again, and then we stop emulation at the second time that we hit 7C00. So at this point, the original contents of the MBR should reside within our emulator's memory. Okay? It doesn't matter if it's stored encrypted 5 times on disk. I mean, we're still emulating through the decryption loop and everything. So we get it for free. And sort of similar for the other case, if it's, when it's either the VBR or the IPL, it's just that you let emulation continue all the way until you reach boot manager. And then you just replace everything in that emulator memory to write that back to disk. So it's not hard at all. And obviously, yeah, just reboot to finish, reboot the system to finish it off. So just finally, I'd just like to discuss like a few challenges with this approach, because I really like it, but as most detection techniques, it's hard to find or come up with like a silver bullet that will work in all cases. That's like just the way it is. You need to combine various detection techniques and approaches in order to sort of get all the edge cases and everything. So for non-standard bootloaders, so such as grub, if you install grub on Linux, you can do like a dual boot thing. So you will get this UI up where you can sort of choose which operating system you like to start. So if this is running on the system, I mean, we can sort of fake keyboard input, but it's really hard to make the decision of which OS to run. And similarly, if you're using the full disk encryption solutions, where the user is expected to enter a password at the very start, then, well, you don't know the password, so, I mean, you will just fail. And another issue with the full disk encryption things is that they also normally hook interrupt 13, because they want to decrypt the contents of the sectors or disk as they're being read into memory. Otherwise, the OS would never boot. So it's hard or impossible for us to make decisions. But what we can do is to detect if this may be a problem. Because whenever the boot code will ask for user input of some sort, it will issue an interrupt 16 to poll for keyboard input. So since we've registered an interrupt handler for that, we can actually at least, we can abort emulation and just report that, hey, I can't do anything on this system, try some other approach. So just in conclusion, I'd like to just reiterate that anomalies in the boot sectors, they are detectable by emulation. It works really good. But you need to incorporate some anti-rootkit techniques in order to make sure that you're reading the true contents of the sectors on disk. It's really efficient at countering like obfuscation and encryption, that sort of stuff, because you're just basically emulating through the code that will do the deobfuscation or the decryption for you. So it's not really a challenge. But it does have some challenges with the more non-standard bootloaders. Fair enough. If you want to break the rootkit or disable the rootkit, just break its load chain. And again, just emulation is really nice for a nice efficient way of sort of retrieving the original one in order to enable you to do that. And as a final claim, I know that there's been some vulnerabilities found in UEFI systems lately, but I would still claim that, at least on paper, that UEFI systems should be more secure than BIOS systems. Because, if you're booting from signed firmware where you can be sure that every module that's being loaded during boot time is trusted, that's much safer than, relying on technology from the 1970s where, we can manipulate parts of them. So with that, I'd like to say thank you very much for your attention. I'd like to give a special thanks to my co-researcher, Leif Arne Söderholm, who's been a part of the research behind this presentation. So I'd like to give a high five to the rest of the team. And finally, I'd like to also give a big thanks to the guys at kernelmode.info, which is a forum. It's just a great source of rootkit samples. Been using it quite heavily over the years. So yeah, as a final remark, please fill out your feedback forms. And if there's any questions, then please talk. Thank you very much.